You're on.
And our next speaker will be Thomas Gibson, talking to us about hybrid mixed compatible finite element solvers for numerical weather.
Thank you very much. I would like to thank the organizers, David and Lawrence, for putting together this meeting. It was very fun and exciting to meet a lot of different people here, share ideas. I would also like to thank Rob Kirby for giving about half my talk, but it's okay. So I specialize in these hybridized techniques, these hybridized methods for mixed problems, for a special class of discretizations, for NWPD, numerical weather prediction. And so the reason I'm interested in this, it starts back with a conversation between some researchers at Imperial and the UK Meteorological Office starting this project called the Gung-Ho project. And the core of this project, the core idea is to sort of move away from these orthogonal grids, which are used by these staggered finite difference techniques for dynamical cores, which run their weather prediction software. And as you can see here, the pole problem, which is the problem where the uniform grid lines converge at the poles, destroys the scalability performance of being able to drive their software onto massive parallel machines. And one way we can avoid this is to use a non-orthogonal mesh. So we run into the territory finite elements, which are, for all intents and purposes, are shape agnostic when it comes to the choice of cells. You still have poles. In fact, there's a nice little well-known algebraic topology theorem called the Hairy Ball theorem. That is not a joke. If you're on Wikipedia, go look it up. It exists. Basically,
How you Google that.
yeah, well, yeah. Basically, the idea is that you can't avoid having poles. However, if you're using an orthogonal grid, such as like an icosahedral sphere or a cube sphere, your poles are distributed in such a way that they don't become these resolution attractors at the poles, such as the uniform grid lines. So this is one escape. So ultimately, the goal is to devise a finite element scheme for the full compressible atmospheric equations. In this case, these are your compressible Euler equations on a rotating sphere. And the framework we use is this class of compatible finite elements, which are a special class of mixed methods which have very, very important conservation properties, preserving the physics, really, of the underlying governing equations. So what really drives this is this finite element exterior calculus framework. It's a bit like beer in that you try it the first time, you don't really like it. Keep trying it, it's more and more interesting. So the exterior calculus framework, I really like it. I think it's a very rich mathematical theory. For the three-dimensional complex on a sphere, you can get this nice sequence of cohomologies, a sequence of basically a de Rham complex, as well as its discrete equivalent in terms of the finite element spaces, which you construct your approximations to the various prognostic variables. H1 for like streamlines, H curl for vorticity, H diff for your velocities, L2 for pressure, as an example. And these atmospheric grids are typically constructed from these tensor product meshes. So this is an unstructured base mesh of a sphere extruded upwards vertically to create this structured vertical grid. And these are typically the shape of these atmospheric domains. And what's nice about you can construct the 3D complex by just taking the tensor product of a one-dimensional or two-dimensional complex with a one-dimensional one, which gives rise to these tensor product finite element methods. And yeah, they're compatible, and they give out these properties, these mimetic properties, which are analogous actually to the C-grid staggered finite difference techniques for finite differentizations. Preserving these vector calculus identities below. If you want to know more about that, we can have a chat about that later. So yeah, as I said, typical atmospheric mesh, extruded upwards. So this is, they're characterized by their very small aspect ratio. So we're talking about a sphere with a radius of over 6,000 kilometers with a vertical lid of about 80 kilometers. So these are very thin elements in an atmospheric domain. Much of the much of the stability is actually dominated by the horizontal waves that move through. Although you can't neglect what's going on in the vertical. That is a subject of ongoing work. I'm going to stick to a fairly simplified model. I'm choosing this problem because it's simple enough to get the message across, and it captures many of the properties that you would see in a nonlinear model. So this is a linear Boussinesq equation with rotation. And you have a velocity, a pressure, and you got a thermodynamic variable, throw in a buoyancy there. So the compatible finite element discretization of this, you take your velocities in W2, your HDiv space, pressures in L2 space. Now for the buoyancy, there's a bit more flexibility here. But what's done in finite difference codes is they'll use a vertical staggering of some kind. And for example, a Lorentz grid would collocate your buoyancy term with cell-centered pressure. So this would be like taking buoyancy in an L2 finite element space. But actually, this grid supports a computational mode, which is exacerbated by fast-moving waves. And that's exactly the kind of dynamics that these equations support. So we don't want to do that. So instead, they'll use what is called a Charney-Phillips staggering, where your buoyancy terms, your thermodynamic variables, are collocated with the vertical components of your velocity. So this gives you this funny element here, which is horizontally discontinuous, but vertically continuous. The real takeaway message here is you end up with this 3x3 linear system that you need to solve at every time step. And if you're doing a nonlinear method, so let's say you're discretizing the big compressible Euler equations, you'll have some sort of nonlinear iteration, and if you're using, let's say, like a Picard method, you will solve a similar system, a bit nastier, but similar in structure in every Picard iteration, for example. So you'll need to solve that multiple times in a time step. Now, so what's typically done in, say, for example, the Met Office is you can eliminate buoyancy point-wise by doing just a substitution into the equations to get this mixed saddle point system. So basically, for each time step, you can solve for your velocity and your pressure, and then do a simple mass solve to back out your buoyancy. And the mass solve is no problem. The real bottleneck here is this HDiv L2 velocity pressure system. And if you want to build a block preconditioner for this, you have your standard full, Schur complement factorization. Your Schur complement is dense, it is elliptic. And actually, if you include, so in 3D, I'm including the Coriolis term here. Most models actually do not. They will take the Coriolis and they'll treat it outside the implicit solve. I'm including it here for, I guess, generality. If you do include it, though, your operator actually becomes weakly non-symmetric. So there is some issues with the Coriolis term, which can be addressed. But basically, if you've got no Coriolis, this is just good old-fashioned SPD, elliptic Schur complement preconditioner. But because you have an inverse of a dense HDiv mass matrix-like term, you don't ever fill that. You just don't. You do not fill that up. It's a very dense operator. Right. So Rob already went over this. I'll just repeat it very, very quickly. Basically, with hybridization, you break the HDiv space, which means your normal components of your vector fields are no longer continuous between mesh interfaces. And you impose this, so you've lost this continuity in your function space, so you impose it weakly by introducing a trace space or a set of functions defined on the interfaces of a mesh. And when you go back and choose your velocity in this broken space, you'll pick up these surface terms in the integration by parts, and you'll end up getting these surface terms here in your momentum equation. Lambda is a pressure approximation, and in order to close the system, you weakly impose that the jump or the normal components of your broken velocities are continuous. So this gives you I go from a velocity pressure buoyancy system to a velocity pressure system, and now I've got a velocity pressure trace system. So I'm just sort of jumping back and forth between larger, smaller systems, but there is a nice property with this kind of discretization. So Without hybridization, your mixed system has the usual form of a typical HDiv L2 type system. Hybridizing it, you've blown up the degrees of freedom. However, everything is block structure. So you can actually form the short complement of that block system for the trace variables by assembling a sequence of local short complements. And this can all be done element-wise. And that is your only globally coupled system. So you only need to globally solve for the multipliers. And once you have that, you can then go back through the cells and solve a sequence of local linear systems to back out your velocity and your pressure. So that's the key thing here. So Firedrake is already built on this, you have this high-level representation of being able to describe your finite element problems. UFL provides us with that, so we can easily express the finite element forms in the hybridized form, for example. And I've introduced this, I've developed this in the first half of my PhD, this bit of software in Firedrake called Slate, which provides a linear algebra context for doing dense linear algebra on finite element forms. To invoke an instance of a Slate object is you just wrap your UFL, whatever it is, into this tensor object, and then from there you can construct expressions which do things like, I don't know, you want to invert a matrix onto a vector locally. You want to write out a system of equations. You want to solve this using Cholesky or LU in each cell. This is what this framework enables you to do. So, yeah. For example, so basically what happens is you have the math that you want to do. I want to assemble this system for lambda in the hybridized formulation by spinning over every element and eliminating the velocity and pressure degrees of freedom onto the right-hand side and assemble a local short complement to get the operator that you need, so the forward elimination stage. And, well, this is basically just a translation of this math into a high-level Python code. You have your 3x3 block tensor. You can extract out the block corresponding to this, so your fields are enumerated 0 and 1. You can invert that onto a right-hand side or a column-wise or a column block vector. And once that expression gets passed down, code gets generated for that. So it's very, very similar to UFL in the sense that you send UFL to a form compiler and it gives you the local assembly kernel for at that particular element. This one will take many assembly kernels, however many there are that you just happen to be sending in, and it'll assemble your block tensor, and it'll perform the sequence of linear algebra operations that you specify. And this pretty much, it is what it is. That's what it does, and you can do quite a bit with that. So now I want to convince you that hybridization it's a solution approach, but it's a preconditioner in the sense that LU is a preconditioner. It's got a very, the application of an inverse is a very good preconditioner. The multigrid was first introduced as a solver, and you can also use it as a preconditioner for a Krylov method to accelerate your convergence. Hybridization, if you sort of break it down algorithmically, I think it fits very well into this preconditioner abstraction that Petsy already carries within its package. Basically, you can break it down as, well, you're given a mixed conforming system. You break the space. You locally eliminate and do the forward elimination basically you're doing a static condensation to get your global solve it approximately or directly. I don't know, it's up to you. And then take what you've been given, what you solved for, and then just solve the local element problem to get your original variables back. Now, these variables live in hybrid space, or these broken space, but you can very cheaply and quickly inject it back into HDiv. You don't have to do a mass solve. You can actually do this with a little averaging trick that Colin and I came up with, so it's very, very cheap. And that's exactly what happened. So Lawrence already gave an overview on how we introduce auxiliary operators into Firedrake to compose that and introduce our own preconditioners. And I've done the exact same thing, but rather than taking the operator and reintroducing my own operators, I instead take the information about the PD that's already contained and I break it and then I fix it by introducing these multipliers. So introduce your discontinuous variables, get your traces, condense. So I'm setting up my operator here by condensing out the interior unknowns here with this expression. I now get a short complement operator, and I create a KSP for that. It's the only KSP you'll need. And then in the application of this preconditioner, you execute the static condensation, you solve the global trace system, and then you do the backwards reconstruction, and that gives you your approximation. So, and you invoke it just simply by PC type Python, and you can use the hybridization PC from there. Yeah, here's some example solver. So it composes very well with what's going on in PETC. It's very easy to use, I think. I don't automatically check if you should be hybridizing something. That's a math problem, not a preconditioner problem. I mean, so this is, you can throw in any sort of HDF. I mean, we've used this hammer on many, many nails in FireDrake, and you can pretty much hybridize any conceivable HDF L2 problem that you can think of, so long as it's, I don't know, maybe someone in here can come up with their own, and we can just try to take a whack at it with this, so we'll see. Right, so some results. So again, back to the numerical weather prediction. I set up a test problem. I'm using the mixed Ravier-Thomas method of a lowest order, so lowest order Ravier-Thomas method, and a next to lowest one, just an order up. And I have my grid. So for the lowest order method, I chose the number of cells such that I could get as close to what's going on in operational models. So this is about an 87 kilometer resolution, and I have an 80 kilometer lid with about 64 vertical levels. And for the next to lowest order method, so I could fit this on one compute node, I increased the resolution a little bit just so I could have a somewhat smaller problem. But yeah, so the big thing here is that we have these velocity and pressure degrees of freedom. Lowest order, it's about 18.4 million. For the next lowest order, 7 million-ish. And I ran this on a full compute node at Imperial at 20 physical cores. If you want more details, we can chat about that. There we go. All right, so some solvers. I'm using a short complement preconditioner, approximate, and I'm wrapping that with GMRes. In the elliptic solve, I wanted to try two things. I wanted to just do a single whack of AMG on the short complement, and I also tried one where I have a Krylov method, like the conjugate gradient method, preconditioned with that same multi-grid preconditioner. This is just with GAMG in PETC with Chebyshev accelerated ILU and the levers on the different levels. And for the relative tolerance, I solved a 5 digits of accuracy, which is typical in atmospheric models. For the hybridized one, no outer solve, actually, because you can show that if you solve things exactly with hybridization, it's in the trace system, and you basically have LU. You're solving the system directly. So you can actually show that the solution of the hybrid problem is equivalent to the mixed one. So there's this is proven by Arnold and Bretzi, actually. But basically, if you set an outer tolerance, and you can verify this experimentally, if you set an outer tolerance, which is the same as your inner tolerance, you will converge in a single application of GMRes when you apply this hybridization preconditioner. I found numerically that the accuracy in your multipliers ultimately determines how much your residual gets reduced. They correspond. It's kind of neat, I think. Yeah, and I did all the local inversions with LU. So now this is without Coriolis. And that's one of the reasons why I wanted to start without Coriolis. So what I did is I ran through an array of current numbers. So the implicit current number that are typically used in operational models are around, I don't know, 4, 8, maybe 10. I haven't been given a concrete number. I've just sort of heard these magic numbers in the grapevine. But what we want to see is that the execution time remains as constant as possible over this wide range of current numbers, which demonstrates that your simulation is stable. You have a good multi-grid solver, effectively. So hybridization, the green one, I was very happy with that. Still am. it seems to be pretty robust, even when I'm pushing well beyond the critical current range, so up to 32. Now I push it further, 64, 128, and you eventually get garbage. It just becomes too difficult to solve. But I think that's a pretty good range. I thought it was a bit interesting how if you try to use a Krylov method on the inner Schur complement for the approximate Schur complement method, it seems to, I mean, the lowest order one does all right, but it kind of goes a bit, starts to lose its thunder, I guess, as you keep increasing the current number, so you keep getting a more difficult problem. And here I've measured effectively the average iterations required. So right here this is the inner elliptic problem for the approximate Schur complement, and here is the hybridized one, so the hybridized trace operator. It remains fairly constant. I mean, it oscillates a bit. But the thing here, though, is what's killing the first method is that as you increase the current number, it is taking more and more outer GM-res iterations to sort of smoothen everything out. And to get it down to the specified tolerance. And in terms of solver time, there's a variety of ways I could show this information, and I'm trying to be visual. I've normalized the execution time, which is the profile that you saw in the first bit, against a hybrid one, so that so the hybridization is at unity, and you can show it. Well, you can clearly see, I guess, how slow the approximate one is compared to the hybrid one. It's about 3 times as slow. And it also breaks down, I guess, what bit of time is spent in which part of the procedure. So the hybrid one, and this is your pre-only one, which is the competitive one compared to the first one I just showed earlier. Hybridization is solver dominated, so this is a good thing. The time it takes to perform the forward elimination, which is the assembly of the right-hand side, as well as reconstruction, takes approximately-ish the same amount of time. They're both dominated by inverting a local mixed system. That sliver on the top is exactly the projection to get everything back in and out of the hybrid space. That takes basically no time. For the next to lowest order method, hybridization improves even more. This is primarily because I think we're starting to see the benefits of static condensation as you increase the approximation order. Now, so this last one, basically same sort of solver so this is with Coriolis term now. I mentioned that the operator that you get is non-symmetric. So the hybrid one, your trace operator is no longer symmetric, but it's weakly non-symmetric because of the diagonal coupling of the Coriolis term. So instead, I'm using bi-CG stab, and I'm using AMG. Well, you can't use Chebyshev because, again, you need a symmetric operator, but I'm just using Richardson ILU on each level, and I wanted to see how this works out. So again, with the GM-res, I'm just using a diagonal approximation to the velocity mass to get my short complement. Right. Hybridization remains constant. Great. This is still a work in progress. I still need to explore a bit more on what better solver options I could be using here, but at least it seems robust enough. This, I think I can explain now. I have had to think about this. So with Coriolis term, if you're using a diagonal approximation to the velocity term, you're not going to capture the effects of rotation. They appear in the off-diagonal block. So if you're just extracting the diagonal and using that as an approximation to the inverse, you're not going to capture that. And so the operator, that Schur complement, if you think in terms of in the continuous space, it's approximating an elliptic problem with rotation effects, with a factor of delta t times your Coriolis term. Now, as you increase delta t, this bit that you're missing is getting larger and larger and larger. And you're basically getting a bad pressure approximation, and then you get an even worse velocity approximation. So GMRS has to work much harder to smooth everything out. This, I think, explains why it does so well at the lowest order. It's a bit of a mystery to me. But if you just increase it up one more, it starts to go wrong real quick. Again, I'm approaching the end here, so you can reproduce everything that I've done. I have a repository which has all the run scripts. You can see the raw data that I've collected if you're interested. Hybridization seems promising, but I think we can keep doing better. So we're not exploiting any of the tensor product structure, which I think we could do, especially for some of the dense linear algebra. We would ideally like to eventually bring this into within the context of robust matrix-free solvers, so using some sort of geometric multigrid on the trace system. And the one that we have in mind is something that I'm working actually with Eike Mueller at University of Bath, is to use this non-nested approach where you take your trace space and restrict to a P1 conforming problem. This makes sense because the operator, the trace operator, actually approximates an elliptic pressure equation, which you can then approximate with a P1 correction. And this is this multi-grid approach here. I can show you the reference later. There's still some fine-tuning and some analysis that needs to be done. The impact of the Coriolis term, which is not typical. Like, people don't do this in atmosphere simulations, but I think it'd be worth at least just taking a look on how the Coriolis term is affecting things. And then there's the issue with optimal scaling for Richardson. So you have this dampening factor in the Richardson method, which you can turn on scaling in PET-C for some of the harder non-symmetric operators that I have. However, I found that the default one, which is 1, I believe, tends to work. It's still not good. It'll work. But I had a peek inside the code, and I suspect that the computation for the optimal dampening factor relies on the matrix being SPD. So if there's a way to do it for non-symmetric operators, I would like to definitely know. Right, where is this all heading? So I'm not just doing linear Boozenesque. Colin and I have been developing a hybrid method for the compressible Euler system, the full nonlinear one. So this is a work in progress. We are at the point now where we have a working semi-implicit solver for the full atmospheric equations. But we still have several analysis questions that we need to answer. Well-posedness, stability, and can we get a good multigrid solver for this very non-symmetric operator that comes out of this formulation. So this one is very non-symmetric, even if you neglect Coriolis. It's just, yeah, it's a bit of a wonky operator, but it smells elliptic. So we think it should still be elliptic, but that remains to be shown. Right. So in summary, this is all available through FireDrake. I have to do this branding and all that. FireDrake's great, though. Seriously, you should check it out. We do hybridization, static condensation. So I've shown you stuff for hybridization, but you can do static condensation for CG problems. You can do local elimination for discontinuous Petrov-Galerkin. You can do HDG, the hybridizable discontinuous Galerkin methods, which is actually something that I started working on with, again, Eike Mueller at the University of Bath, and Lawrence as well is getting behind this. Yeah, so ongoing work, extensions to the 3D equations, the full compressible equations are underway. There's also the question of, can we optimize the dense linear algebra that we produce? So this is another problem that we might run into later on. And can we also generate smarter code? So can we do vectorized linear algebra? Can we do nonlinear local solve? So maybe you're solving a PDE which has coefficients that depend on a nonlinear PDE, and you need to do a sequence of Newton iterations in each element. This could potentially be the foundation we need to do that. And you should also check out Gusto. So Gusto has not been advertised very much, but it is a FireDrake finite-based dynamical core toolkit built on top of FireDrake, which uses these compatible finite element discretizations for doing a variety of different simulations for the atmosphere. Shallow water, Boozenesque, incompressible Boozenesque, compressible Euler, we got it all. Well, if there is more for atmosphere, maybe, I don't know. Right. I think I'll leave it at that. Thank you very much for listening.
Time for questions? Matt?
So, what would be the argument against using eigen to handle those very small dense linear?
Yeah. Okay, so the question was an argument against using eigen. So eigen is currently the linear algebra backend that we're using when we generate the code. So I can tell you a reason why eigen was chosen, in that it's, despite it being this sort of a bit complicated of the templated C++ library, they are a bit flexible in how you can do your linear algebra. It just seemed like a pretty easy thing to generate on the fly, and it turned out to be fairly straightforward. As for why, what are the, I mean, what are the alternatives for very small, dense algebra? I don't know of any alternatives.
No, we do use eigen.
We do use eigen.
And that's the plan going forward. When you say it's
Ah.
ongoing work, I thought you were going to do something vectorization.
We're talking about vectorization.
So then there is
Yeah.
a problem with eigen.
Yeah.
And the problem with eigen is, so if you're on not very high order, and actually even if you're on moderately high order and you've done your sum factorization homework correctly like we have, then you don't have long enough loops inside your vector, inside your elements to absorb your vector lengths, particularly once we start going to 512 bit vectors. So TJ is working on stuff to have Firebreak assemble multiple elements at once in order to suck up the vector lengths and vectorize properly, which for moderate order matters because you are still flop limited in assembly. But then you want to do this stuff, and all of a sudden you dump into the local linear algebra, which also doesn't vectorize very well. At least the solves don't vectorize very well. And so in an ideal world, you would run multiple small solves at once. And
like the packed logic.
sorry?
So like the packed logic. That's what it's designed for.
Right, well you need packed LA pack really, right?
Yeah.
So is that a thing? That's there.
People have given presentations on it.
So yeah, we basically we need something like that.
I have another one.
Yeah.
Can you go back to when you're talking about what you're doing with IT? So for this, that restriction prolongation that gets you to and from T1, are they more sophisticated than easy interpolation?
Yeah, so you mean going from trace to P1?
Yeah.
Oh, actually, they're just L2 projections.
Oh,
They're, yeah. So, yeah, it's not too bad. What's nice I mean, you're taking this trace problem and going to a CG P1 conforming problem, which you can slam with the wide array of tools that we already have out there for that. So that could be a way to speed up the global solve.
do you guys say auxiliary space for that?
I'm sorry?
Is that what the same thing as what people say auxiliary space for?
I don't think so, no.
Oh,
Any more questions for Thomas?